Let's now discuss the energy of an inductor. So the idea in here is that the inductor can store energy and then give it back. So as a result, we would like to understand how this happens and what's the amount of the energy that it stores. So I'm just going to consider a circuit, an arbitrary circuit actually. It doesn't matter what the circuit is. It doesn't even have to be an LR circuit, so there can be something else in there. So there's a circuit in there, but I'm not interested in the rest of the circuit in here. So I'm just going to show it with a black box thing. So somehow this inductor is connected to that circuit. Let's say that the inductance is L. And at a given time, let's say the current passing over this is I. So the current can change in some other ways as well. It doesn't have to be decaying. It might be... This might be an AC circuit, for example, in which case this is sinusoidal. So I don't care about that. So let's just remember again that this inductor is actually equivalent to an EMF device. There's an EMF in there. So again, I'm not drawing the rest of the circuit. So you can think of it as an EMF device. So the current is there. And let's remember what an EMF device is. EMF device is a device that provides energy to the charge carriers. It gives energy. Well, there's certainly an energy exchange between the charge carriers and that device. So as a result, we have to understand this inductor therefore as such kind of a device. And at some point, we have written down a formula for the amount of the energy transferred from the EMF device to the charge carrier. So let's just write this thing down. This is a power expression. So this is the power of energy transferred from the inductor, which is an EMF device. It's actually an EMF device. You can think of it like that. Power of energy transferred from inductor to charge carriers. So the power is, of course, let's remember that is the energy per unit time. So it's basically the current multiplied with the EMF. So that was the expression. And this is the one that we are going to use, of course. So let's just say that, this is the EMF device in here. That's the inductor essentially. This energy goes out from the inductor and then goes to the charge carriers in here, which are these invisible particles which are moving inside the wires. So let's just keep this in mind. So that energy is added to the energy of the charge carriers and subtracted from the energy of the inductor. So let's just think about it like that. But just keep in mind that this can be negative too. It doesn't have to be positive, especially for an inductor. The energy exchange can be in two ways. So as a result, when we are writing down formulas like that, you should be clear about everything. You don't have to assume anything about the sign of these quantities, whether the EMF or the current can be of any sign. So the final result can be positive or negative, but at least as a formula, this is the correct formula. So therefore, let's just remember that this EMF is given as minus L di over dt. So therefore, the power is equal to I times the EMF, which is therefore minus L times I di over dt. So that power is transferred from inductor to the charge carrier. So the rate of change of the energy of the charge carriers, if you want, the energy of the charge carriers divided by time, delta t, right? Delta E divided by delta t is equal to that quantity. But if you want to compute the energy of the inductor, so let's say it like this. This is the energy of inductor. Inductor is actually giving that energy. So therefore, the rate of change of energy of the inductor is equal to, is the negative of that power. So therefore, this is equal to plus Li di over dt. Right? Again, this can be positive or negative, but at least formula has a plus sign in front. So it's a big plus, so let me just erase it. So it's just a positive sign. Sorry about that. So, and then we can integrate it. So therefore, if I integrate this power, this rate of change of energy expression with time, sorry about that, the inductor's energy divided by the change in time, that's going to give me the change in the energy of the inductor. So therefore, this is between some initial time, let me write initial and final in here, of L times I di over dt multiplied with dt. This is actually a symbolic integral, but I mean, we can see by using the techniques that we have learned from calculus that we can easily manipulate these kind of expressions. So I can express this not in terms of time, but the current. And in that case, L is just a constant and current is the only variable. And you can see that the integral of this thing is I squared over 2, but it has to be evaluated between this initial and the final times. Right, so therefore, change in the energy of the inductor is equal to the change in this quantity 1/2 of Li squared. So if you just think about some final time and an initial time, so therefore this change in the inductor's energy is the final current squared minus initial current squared. Let me erase and rewrite these because these letters did not come out correctly. That I subscript does not look nice, but in any case, I have a change in an expression between initial and final times on the left-hand side and on the right-hand side as well. So it's natural to expect that this final quantity is equal to that final quantity plus a constant 2. So therefore the inductor's energy therefore should be equal to 1/2 of Li squared plus a constant. Just remember that we can always add a constant to energy, so that's not going to change anything. But instead of dealing with these kind of constants all the time when we discuss the inductors, we usually choose this to be a simple nice value. So it's actually quite nice to choose the energy of the inductor when the current is 0 to be 0. So as a result, choose this to be 0. So then we say that the energy of the inductor when it is carrying current I is equal to 1/2 of Li squared. When it is carrying, when there's a current I flowing on it. Is given by that expression. So 1/2 is actually a factor that appears in most of these expressions. The important thing is that, of course, this is quadratic, it's a square. In most of the simple energy expressions, we also have these like the kinetic energy of a particle, potential energy of a spring, for example, or the potential energy of a capacitor. We have the square of a variable multiplied with a constant, and then there's always a 1/2 factor. So these are kind of common things that appear in these kind of equations. So the 1/2 factor in here is coming from the integral. Okay, so therefore, whenever the amount of the current changes on an inductor, the energy changes. So if we increase the current, then we are adding energy to the inductor, and we try to decrease or we decrease the current, then we are taking energy from the inductor. So inductor exchanges energy with the rest of the circuit through through its interaction with the charge carriers. There is a different way of looking at this energy of the inductor, and we can express it in terms of the magnetic field that it has. So let's just look at this. So an inductor an inductor like that. So this is a very bad symbol of inductor. So this is essentially some kind of a device that produces a magnetic field, and so therefore there is a magnetic flux. So just remember that the inductance was the proportionality between the flux and the current. So let's just remember all of these basics. There was only one example that we have computed the self-inductance of a circuit, and that was a solenoid. It's a long solenoid, in fact. So we had these parameters: the length of the solenoid, the number of turns, and the area, the cross-sectional area. So there are these wires in here. Whenever there is a current on the inductor, of course there is a current. The same current is basically passing over these wires. And as a result of that, there's a current, there's a magnetic field produced inside the solenoid. Let's just remember that the magnetic field has this expression mu0 times the number density of the turns, number of turns per unit length, multiplied with the current. Forget about this vector sign in here. I'm just writing the magnitude. So that's inside the solenoid, and the magnetic field 0 is outside. For an infinite solenoid, this is correct. For a finite solenoid, but a long solenoid, this is just an approximation, but we said that this is a good approximation, so therefore this is what we use. So what I would like to do is to express the energy of the inductor in terms of the magnetic field. In that case too, we get a very simple expression. So let's just write this thing down. The energy of the inductor is 1/2 of L times I squared. What was L? I forgot the expression of L. So let's just quickly compute L. So we had this expression, flux is equal to inductance times the current. Let's just compute the flux. Flux was equal to the magnetic field multiplied with the area multiplied with the number of turns. Magnetic field is given like that, so therefore this is mu0 n divided by length times the current times area. So therefore this is mu0 n squared area over length multiplied with the current. So therefore this must be the inductance. So therefore this is mu0 n squared over length times area multiplied with a squared. The current squared. I think I need to write down the current in terms of the magnetic field in here. So let me erase this and then write the current as magnetic field divided by mu0 n divided by L squared. So if we do this, I need to do this in 2 steps. So I get like L squared over mu0 squared n squared b squared. Length cancels one length in here. N squared goes away. I have an area in here and one of the mu0s go away. So therefore this is 1/2 of b squared over mu0 multiplied with area times length. All right, so that's the expression. So let me then erase everything in here. And write this thing down. So therefore this is b squared over 2 mu0. Let me write in the shortened form. So that's an expression that depends on the magnetic field only, multiplied with this geometric factors of the cross-sectional area and the length of the solenoid. All right, let me erase this and this as well. So here then we have the volume I'm going to show this with a V is not a let me write V sol in here, so that's the volume of solenoid, so that we don't confuse it with the potential drop of some other thing perhaps. So therefore the energy of the inductor is a quantity that depends only on magnetic field multiplied with only with the volume of the solenoid. Alright, we are just going to do the same thing as we have done before. So we just call this quantity therefore the magnetic energy density, because apparently it has the units of energy density. So I'm going to call this as U mag multiplied with the volume of the solenoid. So therefore the energy of the inductor, energy of the solenoid is equal to some energy density multiplied with the volume of the solenoid. And the energy density is given as, this is the magnetic energy density, 1 over 2 mu 0 b squared. So that's the magnetic energy density. Right, so this formula is just shown for a single inductor, for a solenoid. There might be some other kinds of inductors, perhaps a short solenoid and I don't know, some other strange shapes perhaps, in which case the magnetic field perhaps would not be uniform. But it appears that in the case of a non-uniform magnetic field, if you just compute this expression everywhere, which is the magnetic energy density, and then integrate this over volume, you still get the same energy. So this appears to be true, that this is something that we cannot show in here. We cannot prove it right now in here, but this is our jumping point. So for this example, we can get this formula correctly, but for all other examples, I'm going to claim that this is going to be true. So for any kind of an instrument, so for any other solenoid, for any other inductor, right? There's some kind of an inductor device in here. Doesn't matter how strange it is. This inductor produces a magnetic field in space. It just produces a magnetic field. As a result of this current, of course, the current that passes over the inductor. So what we do in here is this. If I if I compute this expression, so it's the magnetic field squared divided by 2 mu 0, right? This is the magnetic energy density. And then multiply this with the volume of the, I don't know, inductor, volume element. So basically what I do is I just divide the space into these small pieces, small volumes. That's what I have called as the volume of the inductor. Probably that's not a good thing. So let me just call this as dV, but then don't confuse this with any voltage. This is just the volume. But since the magnetic field is not uniform, I have to evaluate an integral in here. I cannot just multiply with with total volume, so that would be incorrect. So that's basically energy density multiplied with volume integrated. That actually gives the energy of the inductor. And so basically in terms of the inductance, it is given like that. Now we can actually show we can claim that this is true, but as I said, I mean, I cannot show this to be true mathematically. So at this point, we just have this conceptual jump, and we say that the energy is actually stored inside the magnetic field. So the essential idea in here is this: to produce a magnetic field. To create a magnetic field, right, we have to spend an energy. So as a result, when we are trying to increase the the current on the inductor, we are actually giving energy to the inductor because the inductor should produce this magnetic field. But once the magnetic field is produced, no more energy is required. So to produce a magnetic field, we have to spend an energy, right? So that energy is stored inside the magnetic field, in the field itself. So we say that the magnetic field has that energy actually. This is kind of hard to imagine because we haven't. There's this kind of a difficulty in here. The electric field and the magnetic field, these are not material things. They are not formed from atoms. So therefore, anything that's not formed from atoms, we have a difficulty in imagining them. And it's also equivalently harder to imagine that they may have energy. But this is true, so somehow we have to accept this. So this field thing, whatever it is, that thing that fills that empty space, that is present in that empty space, that also carries energy. And it also appears that they also carry momentum as well. In any case, we can get back that energy by destroying the magnetic field. We can get that energy back by destroying the field. Destroying is not a nice word, but I used it in any case because I couldn't come up with a better word. When you set the magnetic field to be zero, you just decrease it and set it to zero. You can get that energy back. So to establish a magnetic field, to increase from zero to a finite value, you have to spend some energy. When the magnetic field is there, that energy is still there. So you can get that energy back when you make the magnetic field to go to zero again. So in that way, the magnetic field stores that energy. So you can also think of it like that. Let me try to remember if there are any other things that I have to state. So as a result, this kind of completes the what we call as electromagnetic energy. If you remember, we have talked about this electric energy density. This is 1/2 of epsilon 0 E squared. So this is the electric energy density. This is also energy density. We have said that to establish an electric field, we have to spend some energy. And then we have this magnetic analog. In that case, the permeability quantity is in the denominator, B squared. So as a result, there is some kind of a parallel between these two expressions. So that's the magnetic energy density. And so therefore, their sum, the electric energy plus the magnetic energy, that's the electromagnetic energy. So there's just not a single field. There's usually both electric and magnetic fields, and both of them carry some energy. So these are going to be given by this. So that's the total energy density of electromagnetic fields, let's say. So because there are two fields. All right, so when we talk about, for example, the electromagnetic waves, this is important because in that case, this is the energy that is carried away by the waves to faraway distances. So, as I said before, it's not just the energy, the fields also carry momentum as well, because somehow they can exchange momentum with particles as well. So they not only exchange energy, but they can also exchange momentum. So as a result, even though they are not material beings, they don't have mass, but somehow they have these physical attributes of the energy and momentum as well. So that's one of the things. The second The last thing is that, of course, when I said about the magnetic field doing no work in some certain situations, it's essentially, I should be talking about this energy density or the total energy of the magnetic field. So if there are situations where that magnetic field doesn't change, in that case, magnetic field does not exchange energy with anything. It can modify, it can apply forces to particles, but it doesn't exchange any energy. But if there are some situations where the magnetic field is changing with time, in which case the magnetic energy density and therefore the total magnetic energy is changing, in that case the magnetic energy is converted into other kinds. So we know that at least it is definitely converted into electric energy, because when the magnetic field changes with time, there's an electric field, an induced electric field, and some of this energy may actually go to the other particles as well. So this is the case when I say that, yeah, magnetic field can exchange energy with particles, but there is this kind of a complicated process. First, the magnetic field produces an electric field, an induced electric field, so just transfers part of the energy in there, and then this electric field somehow transfers part of its energy to the particles. So as a result, there's some kind of a process which consists of many steps. So in general, therefore, the magnetic field can do work by exchanging energy with other things, but perhaps it does not give directly energy to the particles. So there's some kind of an indirect route of energy transfer.